Hello, everybody. Welcome back. This is going to be a little overview of Section 9 out of Chapter 3, Derivatives of Logs and Exponential Functions. We've already seen how we take derivative of exponential functions, especially using the chain rule. So what I'm really going to focus on is just derivative of logs and how we actually use logarithmic properties to help us take derivatives a little bit easier. So first, we'll begin by the definition at the very top of the screen. So in general, the derivative of ln of x is going to equal 1 over x for any x value larger than 0. And the derivative for the natural log of the absolute value of x also equals 1 over x when x does not equal 0. So in other words, we're covering both tracks here by saying x is greater than 0 and not equal to 0, okay? Because if you remember, by definition, the argument of the log cannot equal a negative number. So we're just covering our tracks here. And then the most general definition, and I'll highlight this for us here, because this involves the chain rule. So the derivative of the ln of u, where u is going to be some function of x, is going to be the derivative of u with respect to x over u of x. So let me there we go, make that a little bit easier to see. So let's go ahead and do some examples here. So the first example is just straight up using the definition. The derivative of the ln of x is going to be 1 over x. Now, technically, you're going to multiply this by the derivative of the argument of the ln, which is going to be the derivative of x, which is 1. Or you can just leave it as 1 over x. But with the second example here, you're going to see where I actually use this chain rule. So the derivative of the natural log of 3x squared plus 6 is going to be 1 over 3x squared plus 6 multiplied by the derivative of the argument of the function. In this case, it's going to be 3x squared plus 6, or 6x. Now, if you wanted to, you can clean this up a little bit by writing 6x over 3x squared plus 6, and that's fine with me. You could factor out a 3 and simplify even further. I'm not going to worry about that. I just wanted to set up the derivatives, that's all. Here's an example here where we're going to have to use our product rule. So if y equals x squared times the natural log of x, find y prime. So you can see here we have two different functions of x. So I'm going to call this f. I'm going to call this g. Off to the right, f equals x squared, therefore f prime equals 2x. G equals the natural log of x, so g prime is going to equal 1 over x. So y prime is going to equal f prime g, so that's going to be 2x times g, which is the natural log of x, plus f times the derivative of g, which is 1 over x. And if you wanted to, you can clean this up a little bit just by saying 2x ln of x plus x, because x squared times 1 over x simplifies down into just x. All right? Now, what we could do here is we can transition a little bit to say, okay, well, we've seen e to the x, but what about like just basic power or exponential functions where b is not going to be the letter e? Let's say it's like 3 to the x or 5 to the x or something. So real quick, we have our little definition up at the top. Oh, let me go back to black, sorry. So the derivative of b to the x is what we're defining here. So if b is greater than 0 and b not equal to 1, then for all x, the derivative of b to the x equals b to the x times ln of b. Now, in a previous video, I kind of went over the derivative of e to the x, and I said, well, the derivative of e to the x is e to the x, and I kind of said, just buy into that for a second. Well, with this definition here, it kind of brings home why the derivative of e to the x is just e to the x. So, if I go ahead and I follow my rule from above, my rule says the derivative of e to the x is going to be e to the x times the ln of e. Now, if you recall from your properties of logs, the ln of e by definition is equal to 1. So this is going to be e to the x times 1, or just e to the x. All right, let's look at another example here. So what is the derivative of 5 to the x? Well, that's going to be 5 to the x times the ln of 5. And that's basically it. Honestly, I hate to say it, but that's as hard as it gets. So the next example we're going to be looking at here are going to be derivatives of logs where they have a different base. So if you rewind the video a little bit, we were dealing with ln of x. Well, to be honest with you, the ln is just the log base e of x. So we were looking at a very specific type of derivative. Now we're going to get more general here. So the derivative of log base b of x is what we're defining. So if b is greater than 0 and b not equal to 1, then, and these are, we're just covering all bases here in terms of letting x be greater than 0 and letting x not equal 0. So they're both basically the same. The derivative of log base b of x is going to be equal to 1 over x times the ln of b for values of x that are greater than 0. And it's the same exact thing, except we have the absolute value of x now for the argument of the log. So the derivative of log base b of the absolute value of x equals 1 over x times the natural log of b again for all values, or I'm sorry, not for all values, for x not equal to 0. So again, just follow your property from above. So if f of x equals log base 3 of 7x plus 3, f prime of x is going to equal 1 over 7x plus 3 times the natural log of 3 multiplied by the derivative of the inside function, which is going to be 7. So f prime of x is going to equal 7 over 7x plus 3 times the ln of 3. So you got to use the chain rule here for this, because you have a function of x that has more terms than just some basic monomial, okay? Now, for the last example here, we have logarithmic differentiation. Now, if I wanted to, I could say, find y prime for the following equation. So y equals the quantity x squared plus 1 times e to the x, all divided by x squared plus 4. I could do that, but if you notice, we're going to have to use the product rule in the numerator, and then we're going to have to use the quotient rule down below. And then, you know, if you have to, you got to simplify all of that. And we've seen derivatives where they just expand very large very quickly. So what we can do is we can kind of make our lives a little bit easier. So what I'm going to do is I'm going to apply some of the properties that I've learned back in pre-calc of rules for logs. And one of those properties is actually very, very, very important. And the property is log base b of x to the r is going to equal r times log base b of x. In other words, what you can do with exponents is you can pull them out front. That's the first rule that we could use. The second property is this one, where we have log base b of x times y is going to equal log base b of x plus log base b of y. And then the last property is going to be log base b of x over y, and that's going to equal log base b of x minus log base b of y. So what I'm going to do here is I'm going to use these properties and go ahead and simplify my equation. Now, please note that all these properties also applies to the natural log, because the natural log, remember, is just the log base e. So all the properties still apply with ln's. And I'm going to go ahead and use the ln because it's just easier to use. So let me write down my equation again before I forget it. Y equals x squared plus 1 e to the x over x squared plus 4. So I'm going to take the natural log of both sides first. So I get the ln of y equals the natural log of x squared plus 1 times e to the x over x squared plus 4. And by doing that, what I can now do is I can kind of make my life a little bit easier, because I can apply those properties and simplify the right-hand side. So I'm going to get, once again, the natural log on the left-hand side. So that's going to be the natural log of y equals. Now, in the numerator, I'm going to go ahead and separate them. So I get the ln of x squared plus 1 plus the ln of e to the x. And then my denominator, x squared plus 4, I'm just going to subtract that. So I get the natural log, or minus the natural log of x squared plus 4. Now I'm going to apply one more rule. So I get the ln of y equals the natural log of x squared plus 1 plus, now I'm going to take the x and pull it out front. So that's going to give me x ln e minus the ln of x squared plus 4. And then just to simplify it a little bit further, I get the ln of y equals the ln of x squared plus 1 plus x, because by definition, the ln of e is equal to 1 minus the natural log of x squared plus 4. Now, we're going to take the derivative of this. We know the derivative is dy dx. It's all the dependent variable with respect to the independent variable. So on this left-hand side, when I take this derivative, I have to use implicit differentiation. Okay? So this is going to be the derivative of 1 over y times dy dx, or if you wanted to, you can use the notation y prime as well. That's up to you. Notation is all about what you want, not what I want. And this is going to equal. Now, if you look, I have what used to be a very complicated, let me scroll all the way up, a very complicated looking derivative, product rule and a quotient rule. And I made it into just the derivative of a bunch of ln's, which are very simple, because the derivative of the natural log of x squared plus 1 is going to be 1 over x squared plus 1 times 2x plus the derivative of x, which is just 1, minus the derivative of the natural log of 1 over, or of the natural log of x squared plus 4, which is going to be 1 over x squared plus 4 times 2x. Remember, you're going to use your chain rule there, okay? And I'm going to simplify this just a little bit. I'm going to make it look nice and neat. So 1 over y times y prime equals 2x over x squared plus 1 minus 2x over x squared plus 4. Now, we are almost home free. You got to remember, the directions were find the derivative. So what I need to do is take both sides of my equation, and I have to multiply it times y, because I'm solving for my derivative. So this is going to yield y prime equals y times 2x over x squared plus 1 minus 2x over x squared plus 4. And the last thing that we have to do is we know what y equals. Y equaled the original function from the very start of the problem. So our derivative, and this is going to be final here, y prime equals, well, you got to remember y, you got to remember, I got to remember, y was quantity x squared plus 1 e to the x all over x squared plus 4. So this is going to be quantity x squared plus 1 times e to the x all over x squared plus 4 times 2x over x squared plus 1 minus 2x over x squared plus 4. I'm going to make that look prettier. X squared plus 4. And that is our derivative. So, although this derivative, not going to lie, looks not like the most appealing type of derivative, just by understanding some properties of logs, it makes actually finding the derivative, pardon the pun, exponentially easier than just taking the product rule, quotient rule, and then a bunch of algebra after that to try to simplify. So that's going to be it for this video. We got one more video for this section, and it's going to be 310, I think, derivatives of inverse trigonometric functions. So I will see you in the next one. Later.